So I just noticed it was a little hard to see what I was writing, so I moved the video camera a little bit closer. And now I'm going to erase most of this. And I thought we could actually go over the homework really quickly, which might help you when we get to class. Hopefully this will make it so you don't have too many questions on it. And here's the solutions that you guys will be getting as well. The first one was asking you to look at a figure in your book, okay? And it showed you 3 vibrational modes of the string. It actually showed you F1, which they called A, F2, which they called B, and F3, which they called C. And they didn't have a 4th one in the book. They only had the first 3 harmonics. First it said, how does the frequency of the wave produced in C compare to the frequency of the waves produced in A and B? And it said be specific. So knowing what we know about harmonic frequencies, how does the frequency of the wave here compare to the frequency of the wave here or here? And so the answer qualitatively would be, well, if it's 3 times the fundamental, it's definitely more. And you can kind of see this one, you know, is jiggling faster. To do this, you had to shake a lot faster than here. And in fact, you had to shake 3 times faster than the fundamental. Whereas here, you had to shake twice as fast as the fundamental. So if you're just simply stating that F1 and this is 2F1 and this is 3F1, that's probably fine for answering that question. How many complete waves are shown in each of the cases? And remember, when you're looking at waves, that one complete wave is from a node to a node to a node. So that's one complete wave. It has to have a full up and then a down cycle right after it. Okay, so this would be a half a wave. This would be a full wave. So in the fundamental, how much of a wave is on the string? The answer is a half a wave. So this string length, whatever it is, supports a half wavelength in that vibrational mode. We come over here to this guy, and we say the same thing. How much of a wave is supported here? Well, the length of the string is the same as it was here. It still is long, simple string, but now it supports 2 bumps. So to have 2 bumps on the same size string, the bumps had to get half as big. So now we have 1 full wavelength on the string. And you can see that there's 1, 2, 3 nodes, which means there's 1 full wavelength. And finally in C, the waves got even tinier, right? And so we were able to fit more bumps on the same length string, but now we have 1, 2, 3 half wavelengths, or 1.5 wavelengths. So this is half of a wavelength on the string, this is 1 wavelength on the string, and this is 3 half wavelengths, because it's 1 half, 2 halves. And those all equal the length of the string. So now, in C, part C, you're going to have to calculate something. And it says if the string is 1.5 meters long, okay, then what's the wavelength in each case? And so if we knew that this length in all 3 cases was 1.5 meters, it's just a matter of figuring out how long the wavelength is of each of those vibrational modes. So let's do that. So for picture A, okay, we know that a half of a wavelength fits fully on the string, so a half wavelength spans a space of 1.5 meters. Therefore, lambda of the fundamental is going to be 2 times 1.5, or 3 meters. In B, we know that 2 halves, or 1 full wavelength, fits on the length of the string, so it's equal to 1.5 meters. And that lambda 2 then is just 1.5 meters. And always in the second harmonic mode, the wavelength and the string length are the same because it's 1 wavelength fits exactly on the string. And then C, we know that 3 halves wavelengths equals 1.5 meters. Same length string, but now we fit more bumps, so the bumps had to get smaller. And so lambda of the third harmonic is 2 times 1.5, which is 3 divided by 3, or 1 meter. And you can see that the wavelength of the fundamental is the biggest, because it is the smallest frequency, biggest wavelength, middle frequency, middle wavelength, highest frequency, shortest wavelength, because frequency and wavelength are inversely proportional as long as the velocity of the waves on the string stays constant, which it does because we're not changing the medium. Finally, we get to D. If the frequency produced in the first picture was equal to 400 hertz, what's the frequencies of the other vibrations? Well, 2F1 would then be 800 hertz, and 3F1 would be 4 times 3, which would be 1200 hertz. Okay, this would sound an octave above that. This would not sound an octave above that. So this would sound, in fact, I can make the sound if you really want to hear it. Let's see if I can make it. lot similar to one another, but different from this question. They involve a lot more calculation. Hope you guys are with me and that this is being helpful to you. So I'm just going to erase the stuff that had to do with that problem. I'm going to keep these pictures up because I think it will help. Question 2 now gets more into what a guitar string actually does. So, question 2, in fact I'm going to erase this and put up here that the velocity for a string is the square root of the tension over the linear density, so we remember that. In question number 2, we're talking about a string that's a ½ meter long, which is a little shorter than a guitar string. So this distance is 0.5 meters. It doesn't tell you the wavelength, it tells you the length of the string. And then depending on how it vibrates, you figure out the wavelength. So it's tuned to a tension of 40 newtons, and its linear density is given as 5 times 10 to the negative 4th kilograms per meter. And in part A, they say what's the velocity at which waves travel on this string. And so all you need to do is use our handy-dandy equation for waves on a string, and you get V string is the square root of 40 newtons tension over linear density, which is 5 times 10 to the negative 4th kilograms per meter. And when you calculate that, you get 282.8 meters per second, which is fast, pretty fast, right? So that's why you don't really see them traveling down. It's moving, they're moving really fast. Okay. B says, sketch the fundamental first harmonic, parentheses, of the string above, and what is its wavelength? So we know the fundamental looks like that, right? So I don't need to resketch it here. It's the 1 bumper, 2 bumper, 3 bumper, 4 bumper. This is the fundamental. This is the vibration that determines the note you hear. These actually, it turns out, also kind of happen at the same time on the string, and also do all the other ones that I haven't drawn, and that's what gives the tone a depth and richness, but the overall sound of the note you hear is determined by that fundamental vibration. So, if we know that the string is a ½ meter long, and it's vibrating in the fundamental mode, how much of a wave is that? Half a wave. So 1/2 of a wave, which is always the fundamental, is half a wavelength fits on the string, for a string, equals 0.5 meters. So lambda is a nice convenient 1 meter. Okay? What frequency note will it play? Well, that means what's the frequency of the fundamental? And so we want to figure that out. And if you know the velocity and you know the wavelength, this guy gets you the frequency. So velocity equals frequency times wavelength. 282.8 meters per second equals the fundamental frequency times 1 meter. And we don't need to get fancy with that. It's just that the frequency of the fundamental is 282.8 meters per second. Okay. What are the frequency of the second and third harmonics of the string? Well, you could recalculate using the wave. You could get the wavelength of each and use the velocity of each and calculate it directly, but that's a lot of work. Or you could use the trick that this is just twice the fundamental. So if the fundamental is 282.8 hertz, happens to match the velocity only because the wavelength is 1 meter. This is just twice that, which is going to be 565.6 hertz. And I got that just by doing 2 times that. This guy's going to be 3 times the fundamental, not 3 times this. He's 3 times that guy, and 3 times that guy is 848.4 hertz. Okay? So, sounds kind of like a C, kind of like a C above the C, and this will sound kind of like a G. Okay? Above that C. So that's how you deal with it. When you're given the tension, linear density, you want to figure out, and the length of the string, you want to figure out what string note it plays. Most of the time, you know the linear density and the length of the string, and you want to make it play a certain note. And we saw in the guitar, how do you tune a guitar? Does anyone remember? Yes, you tune a guitar by turning the knobs and adjusting the tension in the string. So by adjusting the tension for a fixed string of a certain linear density and of a fixed length, which ultimately will determine the wavelength, you adjust that, the tension will determine the velocity, which will determine the frequency. Because the length of the string determines the wavelength, the velocity will depend on the tension, and therefore that'll tell you what note you want it to play. So most of the time you want to make it play a certain note. So the last example is really about making a guitar string play a certain note. So let's do that really quickly. And I'm going to actually stop for a minute and check my flip again and make sure that it's still running, so hang on. Looking good. Okay, so the last thing that we're going to do is question 3. Question 3, okay, asks you, it says, well, I have a guitar string that's of a length 0.6 meters. That's the length of it. I should draw it like that. Here's the string. And the length of it is 0.6 meters. Okay? You want it to play a frequency note of 440 hertz. And 440 hertz is a concert A. Okay? Sounds, well, you don't have to see what it sounds like. It sounds like an A. I don't know if that's an A. I don't have perfect pitch. I just made a note. Okay, and you know you want it, if it's going to play that note, you know we're talking about the fundamental vibration. Okay, so A says, what's the wavelength? Well, it turns out if you know the length of the string and you know what vibrational mode you're in, you can easily figure out the wavelength using this relationship. So this is a half a wavelength. Fits on a string that's 0.6 meters long. So lambda is 2 times 0.6 or 1.2 meters. That's the wavelength of the fundamental. Okay. B. What's the velocity? Well, we could come over here and say, well, like velocity is T over linear density, but we don't know the tension, right? Tension, we don't know it, so we can't use that, but we have another equation that relates frequency and wavelength. And we have frequency and wavelength, so we can get the velocity that way. Sorry, that was a little flip. I don't know why I just went, because never do that. Okay, so frequency is 440 hertz. Wavelength is 1.2 meters. 440 times 1.2 is a whopping 528 meters per second. These numbers are generally meaningless, like how fast the waves go back and forth along the string. They're wicked fast usually. They're never numbers that you have an intuitive grasp of whether they're correct or not, so just go with it. They're usually around hundreds of meters per second for waves on a steel or nylon string. Okay, C. You're told the linear density by your teacher, who put the incorrect units, by the way, in the problem set, is 6.2 times 10 to the negative 5th kilograms per meter. I said meter. Hopefully that didn't throw you. Kilograms per meter. And you know the velocity. And you want to figure out, ultimately, how tight you tune the string. And so now we can use our other equation for velocity that has tension in it, which is the tension divided by the linear density, which is 6.2 times 10 to the negative 5th kilograms per meter. And we calculated the velocity this way, so we can now stick it in for velocity there and get 528 meters per second and square it, multiply this dude up there, take that, and you get that the tension, I just said dude, I don't know why, is 17.28 newtons. Which is not a lot of newtons, but you could measure that and you could tune the string to that. And if you did this, if you set this whole thing up, got a string, measures linear density, hooked it up between two things, did all of this, tuned it to the right way, and wanted to make it play that note, you tuned it to that tension, you plucked it, it would play that note. And that's pretty cool. That's why I love the physics of music, because you could totally make musical notes purely based on mathematical formulas. All right, so that's the homework. Hopefully that clears some things up. There's a few more things I want to say about this that are pretty cool, but I'm going to need to get this really creepy thing down from the top of the shelf up there, so I'm going to stop the flip for a minute and then I'll start it up.